All right, let's talk about the exponential distribution. So, for a continuous random variable, CRV, x, if its PDF f of x is equal to lambda e to the negative lambda x for lambda greater than 0, we say x follows an exponential distribution. So if we're defining it by its PDF. So graph of that PDF. So lambda is greater than 0 and x is greater than 0. So our graph looks like this. That's our PDF for the exponential distribution. Often with continuous random variables, it's useful to find the formula, if one exists, of the CDF. So remember the CDF, which we denote capital F of x, is the integral from 0 up to x f of t dt. Right, so we integrate the PDF up to x, or we sum up the probabilities up to x. And that's equal to lambda e to the negative lambda x. T. It's a t, because x is on my right endpoint, dt. And then we just have to remember how to anti-differentiate e to the negative lambda t, which is e to the negative lambda t over negative lambda. And we're going to go from t equals 0 up to x. The lambdas cancels, but the negative doesn't. So we have negative e to the negative lambda x minus a minus e to the 0. And so that simplifies to 1 minus e to the minus lambda x. That's the CDF for the exponential distribution. And it's a good one to know. All right, if we want to find the expectation, well, we know that's x f of x dx. That's true for all continuous random variables over the reals, but since it's only non-zero from 0 up to infinity. There we go. So what we have is x lambda e to the negative lambda x dx from 0 up to infinity. All right, I'm going to do first, just for notation's sake, just for the ease of it, I'm going to do the indefinite integral x lambda e to the negative lambda x and come back to the definite after I do this, because this one is going to involve by parts. So we're going to let u be equal to x and dv equal to lambda e to the negative lambda x dx. This means du is dx. This means v is negative e to the negative lambda x. All right, so then this indefinite integral becomes u times v, or negative x e to the negative lambda x, minus the integral of v, so that's now a plus, e to the negative lambda x dx. And that one's a simple integral, so my final indefinite integral becomes minus e to the minus lambda x over lambda. That's it. So that's the definite integral. So if I want to do the indefinite integral, if I want to do the definite integral from 0 to infinity of x lambda e to the negative lambda x, it's this evaluated from 0 up to infinity. So this piece right here, let's just write out what it would be. It's as if x is going towards infinity and is going e to the negative infinity, minus a minus 0 e to the 0. So that first piece goes to 0. All right, and then we have minus got to deal this piece right here. So minus e to the minus infinity plus e to the 0 over infinity. That goes to 0, and we're left with 1 over lambda. Now, one can do integration by parts on e of x squared. So you would have x squared lambda e to the negative lambda x dx, 0 to infinity. And that involves integration by parts twice. And you can easily then show that the variance of x, which is e of x squared minus what we found above, e of x squared, and you end up with 1 over lambda squared. So if we wanted to summarize, if x is exponential and its parameter is lambda, then the PDF, f of x is equal to lambda e to the negative lambda x greater than 0. The CDF is 1 minus e to the minus lambda x. The expectation is 1 over lambda, and the variance is 1 over lambda squared. Those are good things to know.